Okay, good morning, everyone. So, we are in the third session. We will talk today about bifurcations. So, how do we understand bifurcations? You can think about a way of understanding a system. So, if you change a parameter in the system, how does it change? So, the response. If you change a parameter in the system, how does it change in terms of fixed points? Maybe an attractor become a repeller. Maybe a repeller just disappears. Maybe just two fixed points show up out of the blue sky. So understanding bifurcations is a very, let's say, interesting and important way in understanding systems. We can also go a little bit more dramatic and think about terms of stability of systems. This is maybe more, let's say, related with systems of higher order, like second, third order, and so on. But we can still somehow introduce the concept right now, just to make to raise some interest. So right now in the class, normally I would move my hands, but since I don't have hands right now, so I will just show some little figure. I will just in a very somehow schematic way. Imagine here I have a system and I have here a control and I'm somehow controlling the power of the system. And the system produces heat. So this is secondary effect in our machine. It's like in any kind of maybe electrical engine of electronic device. So now imagine that I have a sort of like a bifurcation plot. So maybe as an engineers, maybe we don't know exactly the equations describe the system, but we know somehow how to relate two different parameters. And this is the power, so let's say power, and we have here the temperature, like this. So we may have this situation. We have a situation in which you increase the power and the temperature remains constant. You increase the power, the temperature remains constant, or just change a bit. And a given threshold, let's here at this point, maybe the temperature start increasing maybe dramatically. So in that sense, imagine you have only like a sort of safety conditions under this temperature. So you will say, yeah, I will just try to operate my system in this region. Now, if I go beyond this, at least I know that something is going wrong, and then I will just stop it, or I will try to reduce the power to come back to this somehow safety range of operating conditions. So that would be somehow a case, and we will call it maybe I think this in the sixth session when we talk about supercritical bifurcations. But let's go and be very dramatic. Have a case like this. So again, power and temperature, and then we have here also our safety region. So imagine you think all systems behave like this, okay? So that would be like a happy world because you can somehow predict the future based on the present. So if something is increasing, you can somehow say, okay, we'll keep increasing, then stop. But there are situations in which you have, imagine the same starting point, like this, nothing happens, and in here like a jump, bah, and maybe keep it like this. So this is horribly, this is very, this is tremendously critical for any system because you didn't see it coming. You just, okay, let's change a bit the power, and then suddenly pop, a huge jump. If maybe you will have already like game over, your system is damaged. So this is a system that is not robust. But let's assume that it's actually super hot, but it still is working. So what is the thing you will do when you see this, like you are the guy operating the machine? You say, oh, no, reduce power. and you expect somehow that this is gonna go back in the same trajectory you were just go up. And when your surprise is when you actually start decreasing the power, then this start decreasing, but it's still high. So you are like, oh god, we're still in the dangerous situation. And maybe at some point you will go like this, and at some point, poof, it jump and it go back to this safety place. So in this case, you saw, or let's say you experienced, that you have a path going upwards. So when the temperature increases, and a path going downwards when just the temperature is recovered at the normal operating conditions. And this is something called hysteresis. And you have this situation. And this is of tremendous importance in terms of, if I know my system, I need to know how it changes to parameters that are fundamental for its operation. Okay, so in the class I normally, so this system is basically called supercritical, and this is called subcritical. So in order to make it more let's say less abstract, I will call this thing safe, dangerous. Okay, so as engineers designing a machine, we wouldn't want that the system behaves in such a way, and if it does, at least to understand it and to somehow know the operating regimes of the machine. This is in terms of, this example is in terms of hypothetical machine. For example, it can be actually engine, motor device, electronic device. Let's be, now I keep increasing in dramatism. Now imagine that the system is not just this. Imagine you have a bridge, like this. This is the land, and the land in here. So you have like little cars going in the bridge, and so on. So imagine you have a normal load in the bridge, and all the structural elements in the bridge are behaving like under design conditions. But I think it doesn't exist, to be sincere. Otherwise, it would be very, I mean, it would be horrible. But if you could design a subcritical system, so you could design a bridge to be a supercritical system or a subcritical system. So you can think about the beam, that you keep increasing the load, so maybe more cars, maybe a truck, and then you just see that little by little the beams start to fail, or let's say not to fail, but start to buckle a bit. And then you can somehow establish like safety conditions in which you say, okay, it's starting to buckle beyond the design conditions. Let's remove the load, or let's control the transit of cars, just not it go higher. Of course, this is hypothetical. Bridges, I suppose they are really designed with very huge safety margins. Okay, hopefully. But you can have also a subcritical condition in which you just say everything is perfect. You just go and put maybe something beyond the permitted load, and then you just have a huge buckle and everything fails. And this is the end of the story. So these kind of like sudden catastrophic effects are always coming from subcritical conditions, okay? Because you don't see things coming. They just happen. So you have to know your system very well in that conditions. Okay, so to enter this world, we will just concentrate in one-dimensional systems for the time being. Second order systems will come, so don't worry about that. Okay, so as I said in the introduction, so now we are talking about qualitative changes. So this is it's like a change in the actual flow structure. So in your amount of fixed points, in the nature of the fixed points. And you can classify bifurcations by how the fixed points change in nature or in number as well. So in here, this is a very important one. It's called saddle node bifurcation. This is also be considered for two-dimensional systems. Actually, the name makes sense in two-dimensional systems. Now the name saddle node doesn't make any sense to us. And in this case, we have fixed points that are created or destroyed. So let's see this in a picture. So this is maybe simple to imagine. So you can have as a function that is wavy, so like maybe a very high order polynomial, but at least in the vicinity, something in a little portion in the function, you can describe it as such an archetypal function. So r plus x to the square. This is going to be your archetypal function. And the parameter you are changing is r. So you can see here, so based on what we learned last class, that you have a r that is negative and you have a function like this. This function intersects the x-axis at two different points. The one with the negative slope is going to be an attractor. The one with positive slope is going to be a repeller. So this is something we already saw. Now imagine that you are starting from a negative value, and little by little you're increasing. So the function is actually moving upwards. Okay, like this. So the whole function. Then it's gonna become a moment in which these two fixed points, they will get closer and closer and closer and closer until they collide, creating the so-called half stable point. Thus, this is something I explained last class, that is repeller from one side and attractor from the other side. And if you keep increasing r, so more, then you will see that these two fixed points, pop, they just go away and disappear. And now you have nothing. So in this case, you don't have any equilibrium point at all. So this is a horrible system, because there is no like a point in which the system can be actually stable. Okay, so you have this situation. Okay, and this is how you can picture in your minds a saddle node bifurcation. Okay, just to say, the bifurcation occurs at r0, because in here you can also see it from this direction, there is nothing, and suddenly you just have two fixed points, and suddenly these two fixed points just split in two. So this is something, okay, already said. Now we will have a plot that will be strictly used for picturing the fixed points. So we have here x, r, and we just, for r equal to r1, we just draw the black and the empty dot like this. Now when we go to r equal to r2, there are 2 points that appear. So you can see that these two fixed points are approaching each other. They keep approaching, and at r equals 0, then you will have just a half stable point. So you just like join the dots with a line, you can see this kind of situation. Okay, and the convention is that we will use a fill line, a continuous line, for a stable trajectory of fixed points, and a dashed line for a collection of fixed points that are repellers. So this is how it looks like. So how this so-called bifurcation diagram already summarizes the information of the fixed points for several conditions, so for several values of r. Now the thing is that this is not exactly the way this is plotted in usually in textbooks. Normally what is done is that the independent parameter, so the parameter that we are actually controlling, for example in the example of the electronic device, it was power. So this is going to be the independent variable, and this is why this is plotted in the x-axis. And x, so the value of the quantity of interest, is going to be plotted in the y-axis, in this case x. Okay, so this is just to tell you, so the two typical functions of the saddle node bifurcation. In one case you have a convex function, in the other case you have a concave function, and they just go up and down with respect to r. Okay, this is another typical bifurcation. It's called transcritical bifurcation. In here, the fixed points, they do not just appear from nothing or disappear. They always are there, but they change the stability. And the prototypical, the archetypal function is gonna be this one. Okay, just remember, just before we didn't have this x, now this x is here. And again, you can put a window in the function describing your system and see if it's well described by this function, and then you can actually see maybe how the bifurcation, what kind of bifurcation your system is exhibiting. So in this case we have this function. Here we have a attractor, a repeller. Here this function just goes in here, and you have a half stable point, and in here what it was the repeller becomes an attractor, what was an attractor becomes a repeller. Okay, this is much easily plotted in Desmos. So I will show you this in Desmos quickly. Okay, so we will call a parameter r times x minus x to the square. Okay, now you will see here that Desmos is asking you, okay, so but we didn't define r. You just put add slider, and there you are. So you have r, and you can see here that for negative values of r, you have what? You have a fixed point that is an attractor and a fixed point that is a repeller. Then you keep increasing r a bit. Oh la la, wait, what is going on? Okay, so it increases, and in this moment when r is equal to 0, these two fixed points, they collide, and you have a half stable point. And then, but this you have here still the fixed point that was an attractor, and now will become a repeller, and this one is gonna become the attractor there. Okay, so this is easier way of somehow picturing this in our minds. We will have an example of this in the next slide. So this is a laser threshold. So we will think about lasers. So in the class, normally I will just put a video in YouTube, and you somehow get a feeling, if you don't know it, maybe there is people that already know it, but I didn't know it, for example, how the laser actually is working, and how can we represent the laser threshold by means of a very basic ODE. So before proceeding with the ODE and all this analysis, please go to YouTube, look for a video called How Lasers Work, a complete guide. and you can watch the whole thing, but at least you don't have enough time, just watch between 3 minutes 55 seconds and 12:50. Okay, this is basically what is important to understand the modeling that is behind the ODE I will show you just in the next slide. Okay, so please watch the video. Okay, so let's model this. We have to first think on the variables of interest. So we are talking about what? Laser, which means photons, the how we create photons. So we will call this variable n, lowercase n. And the other important thing is the concept of number of excited atoms. So you remember from the video that as you go on into the process, the number of excited atoms decreases because you are creating more photons, and the excited atoms, they are actually going from this high level state to the ground state as they produce photons. And as we pointed out sometime in the last class, we can then produce an equation for the growth rate of a given thing we are working with, which in this case would be like the photons. So the growth rate of photons, the change of rate, the rate of change, sorry. And then we have here gain and loss. This is the whole model, how it is related to a gain and to a loss. And as I told you also before, I recommend you that you always think in terms of growth rates. In this case also decay rates. So we have here a growth rate of n and a decay rate of n. That's the whole point. Then what is the actual objective? The objective consists in modeling K and R. So the loss is pretty simple, actually doesn't change. So we just say the more photons we have, the higher the chances are that we have losses. Okay, so this is just strictly proportional. And now let's talk about proportionality also in here. So we have here that the growth rate is proportional to what? The growth rate is proportional to the number of excited atoms. So if you have a lot of excited atoms, the growth rate is actually larger. So this is the whole trick. And now the proportionality is gonna be met by a gain. So we will just erase this proportionality and we just put a gain, a constant. And now the last part is how this gain, how this number of excited atoms changes as we go in the process of this laser creation. So the number of excited atoms changes, and we can model this thing in a very simple way, just saying that this is, you have at the beginning a given number of excited atoms, and then as you create photons, then it will decrease in a linear way. Okay, this is another constant. So that's the whole model. Simple, but actually you will see that is pretty able to describe what we are looking for. So we go here in this in our model. So we have the gain and the loss, and we just factorize these things. So we just replace here the description of n, and after some algebra we arrive to this expression. Okay, and from this expression we can already know what kind of function we are dealing with. in here we have, as we pointed out in here, a second order polynomial. Therefore we have two roots. We have one that is gonna be n star equal to 0, and the other one is the one that makes this whole term in here going to 0. So you just rearrange the equation, you will see that the second fixed point is given by this expression. And this is what we just saw before the laser example. We were talking about transcritical bifurcations. And therefore, the parameter you are working here with is n. So this is the bifurcation parameter. So what is the number of excited atoms that I need at time equal to 0? There is a threshold in which I say, okay, I create a beam, a laser beam, or I just create just some radiation of photons all over the place. Okay, so if we go to this point here, so this was the fixed point we were discussing just before. So let me just complete the picture in here. So I mean, there is no such a thing as negative number of photons, okay? But I just want to complete the whole thing so that you can see what is not there, because the transcritical bifurcation is clearly there. So in here you have the function going like this, and this is a repeller. In here is just in this position, so you have a half stable point, and here you go into the change the role of the fixed point at the origin. Okay, so this is the thing. Now when you are in this situation, the fixed point at the origin is an attractor in here, and there is actually no production of photons, so the stable point is going to be n equal to 0. Okay, in this region, okay, this is just the bifurcation, the moment when everything is happening. And in here is just a case when you have somehow a stable beam, because now you have a fixed point that is an attractor and is associated with a positive number of photons, which is the physical thing. So what you have to see is you want that the fixed point, that this fixed point is positive. So this is actually how we describe the threshold, and therefore we say that this fixed point has to be positive, and it happens, you just rearrange the equation, for a given value of initial number of excited atoms. Okay, so this is a very interesting example that just given a very basic as a basic ODE describing actually a very interesting and complex problem. Of course, the whole thing involves quantum mechanics, but the basic representation is valid with this example. Okay, but we are not over yet, because since we are talking about bifurcations, we need a bifurcation plot. Okay, so I will get it with yellow. We have the x-axis, so this is the number of excited atoms, and this is well, the number of photons. Okay, and then we plot it with blue the rest. So there is a threshold in here that is k over g. So before there, the only thing you see in reality is that the fixed point here is an attractor, so you will have just a collection of a trajectory which is an attractor, so this continuous line, if you remember the representation. And then at this moment you will have just the creation of the fixed point that is positive. So now we will go away from the n equal to 0 in this way. Okay, so this is the bifurcation plot related to the laser. Okay, maybe just to complete the whole picture, to make it clear, in here we have then a trajectory of fixed points which are repellers, so we have a dashed line, and in this one, in that moment also we have this trajectory. So maybe just to complement something, you can think this as standing all the time in a single, let's say you just give an excited number of atoms at time zero, you're placed over this line, and then you just think in terms of stability. If I have a perturbation, this particle will go back to this fixed point, which is in this case n equal to 0. But in here, any perturbation in the system with this value of n naught will actually allow the growth, a stable growth of n until reaching this stable point. Okay, this is also shown in the book of Strogatz, figure 333. You can also read the text related to this. Okay, we have another type of bifurcation of interest. It's called a pitchfork bifurcation. In this case, you will have one fixed point that will change the role. So like as before, like in this case, the origin that changed from repeller to attractor or attractor to repeller. But in this case, you will have another two fixed points that exists and suddenly vanish. So we will see this. And this is how it looks like. So remember that the transcritical bifurcation we just saw before, here we have a x to the square. Now we have an x to the cube. And this is the archetypical representation of a pitchfork bifurcation. So for a given r less than 0, you have an attractor. Here you have still like an attractor, and suddenly it becomes a repeller, and two other fixed points show up. Let me just show you quickly in Desmos. Okay, this is the function, how it looks like. Let me do a zoom. And then for negative r, there is just one fixed point. R equal to 0 is still a fixed point. And then you have three fixed points, where you have two attractors, one repeller. So you can picture that in your minds. For r equal to for r negative, you have the origin to be being an attractor. So x equal to 0. And for r positive, you have two additional fixed points that are now being the attractors, and the origin becomes a repeller. Okay, so this is how it looks like. Okay, it's interesting to see this in Desmos as well. So this is the function when we have what? Yeah, two fixed points that are attractors, and the corresponding potential representation is given by the green line. So here are the two attractors and the repeller, and this is also when you change the value of r. Let me just, so this region, which is concave region, that just disappears. Okay, you can play with this in Desmos with your laptops. Now here we have a big difference, and this big difference is just given by one sign. So changing this sign from negative to positive changes this picture. Right now then we have at the same time the origin that is stable, but we have two fixed points that are unstable, and they collapse, and then you have just an unstable fixed point at the origin. Actually, this case is the one we discussed at the beginning of the class that we call subcritical, or in other terms, the dangerous case. Why? So in this case, you have somehow, you are, imagine this is the power again, so we are increasing the power, nothing happens, increasing the power, nothing happens. And in here, there is no fixed point. So this power just goes in this model to infinity or to minus infinity. So it's completely blows away. So a more complete model will add an additional term, in this case minus x to the fifth, as you see here, and this will allow to add an additional branch of fixed points. In this case, this branch in here and this branch in here. And now I have a bound, so like an equilibrium point to go, but still following a subcritical bifurcation. So you see here, so now let's go back to the example. We're increasing power, and in here, boom, it goes away, and now we go to another level of equilibrium. So if this is temperature, we go from 0 to a very large value and nothing in between. And now, as I told you the example before, imagine you want to go back to this position and you think naively that you just decrease power and you just go back in here, but that's not the case, because these cases are somehow ruled by hysteresis, which means that you decrease, but you will stay at these fixed point lines. So this is a stable line, and only until you arrive here, then you will just drop to the case of x equal to 0. So in this case, the temperature are very low levels. So you can see that we have here a hysteresis path. One path when going up in R, and another path when going down with R. Let's talk about this example of a damped bead on a rotating hoop. So we have here a ring, and this ring is rotating on an axis here, and this is the direction of rotation. And now we have a bead. So you can imagine this thing like have a hole, a sphere with a hole, where this ring is somehow inserted. Well, your natural mind will say that, okay, so when you have no rotation, so this omega is equal to 0, you expect, and if you have actually a reasonable amount of friction, you expect that this bead goes to the equilibrium point, which is going to be in here, and they will stay there forever. Okay, now the problem consists in you start increasing the value of omega, and there is a point in which there is a threshold value when this point will not be anymore an equilibrium point, and it will go away from there and find an actual equilibrium point that suddenly, or let's say at some point, shows up. So as you can see in here, we have this behavior of the pitchfork bifurcation. Now let's derive the equations. So the first equation is related to the weight of the mass, so mass times gravity, and is pointing downwards. Okay, and now we will do like a balance of forces over this tangential line. So this is the whole point, the thing we are interested in. We have, imagine you have the rotation is rotating over this circle. Therefore you have a centrifugal force pointing outwards, and it's going to be given by the mass and this distance that is called rho and omega to the square. In addition, we have a force. Well, to be sincere, it doesn't matter where it's pointing out, that is associated with friction. Okay, so well, right now, if we are actually making the rotation in this direction, then we expect that the bead moves upwards, and therefore the friction is somehow counteracting this movement. That's why we pointed or draw this in this direction, like going downwards. And that's all. Now what we have to do is to project these forces on this axis, or in this line we are analyzing and we are doing the balance of forces. Okay, and there is something else that we will ignore, but this is something we will do later. Basically, in addition to projecting these forces, we will see it just in a second, we have this force in here, which is related to the tangential acceleration. So that's why we have here the angle phi and the two dots. So second derivative in time. Second order derivative in time. But as I told you, we will neglect it based on an assumption. The first assumption you can think is maybe friction is super large, and you don't see this term showing up. But in order to make it in a more rigorous way, we will use a non-dimensional analysis. This is also shown in the book of Strogatz, and in that way, by doing this non-dimensional analysis, we can find a condition that make us somehow allows us to apply this assumption of neglecting this term. Okay, so as I told you just before, we just project these forces on this line, and this is what we obtain, and we just write it down. So this is gonna be this balance of forces that reads in such a way. Okay, at this point I will ask in the class normally, what do we do right now? So what is our interest? We have a model here, we have a first order differential equation. What do we do now? So think, please, behind your screens, try to answer me mentally. Send me a signal. Yes, it's actually finding the fixed points. This is the thing we have to do. In order to find the fixed points, then we have to equate this relation in here to 0, okay? And sometimes you will see that is easy to find the roots of this equation if we just make a factorization first. So this relation is factorized in here, and for simplicity, or in order to have a compact notation, we introduce a quantity called gamma that make us the expression simple. Okay, so now we have how many fixed points in there? So the first fixed point is somehow evident. So we're saying mg sinus of phi is equal to 0, and the second one is telling us gamma cosinus of phi is equal to 1. Okay, so what is the function satisfying this? Well, one possible solution can be phi equal to 0. Other one can be 0, pi, and so on. In here, the solution should be what? Phi is equal to arc cosinus of 1 over gamma. Now my question is this function always satisfied? So we can have any value of gamma to find a corresponding value of phi? Well, no. Remember that this quantity remains bounded between -1 and 1. Therefore, we will need that 1 over gamma is what? Yeah, smaller than 1. So remember that this quantity is positive, gamma is positive, therefore we don't need to take into account the absolute value. Well, this means that gamma is larger than 1, or that this quantity is larger than 1. When we go and plot this in Desmos, I already did it and put here the figures. We have something like this. So for gamma equal to 0, we have the fixed point, and this fixed point is stable. So I mean we have no rotation, so the bead is at the bottom of the ring. Here we have a state of rotation when is the moment when the fixed point at the bottom of the ring just loses stability and becomes unstable, and just for larger values, let's say gamma equal to 2 for example, we have 2 additional fixed points. Okay, so now the bead went away from this origin, so from the bottom, and now finds an equilibrium point at an angle phi. So just maybe if you don't remember the whole figure, so it just goes and finds a fixed point, a stable fixed point, a equilibrium condition. So this is a way of representing this with the bifurcation plot. So again, you can see here maybe already the pitchfork bifurcation type. So at a given threshold, so a gamma equal to 1, we have this loses stability, and we have 2 branches that are created which represent the stable fixed points, these 2 fixed points. And if whether you go to this one or to this one depends just on a given perturbation applied to this point. So if you are rotating and it happens that this is perturbed a bit to the right, it will go to the right, otherwise it will go to the left. So right now, I also like that in the book of Strogatz, this is introduced at this moment, the purpose of non-dimensional analysis. And this is just to say, if I have an equation with many terms, I want to simplify it so that I have fewer terms. How can I do that? How can I actually say this term can be neglected? We keep this term on the contrary. So the idea is to compare the size of each term. So if this term is smaller in comparison to another term, I can neglect it. So the question here is, under which conditions can we neglect the tangential acceleration? So in the slides that are also provided in Moodle, I'll carry it out like a formal way of doing non-dimensional analysis by the P theorem, the Buckingham's theorem. However, for the purpose of the class, of this, the message, carrying out such an analysis is actually not super important. So feel free to go on the slides and look at this, but we will just go in a more straightforward way. Right now, what is important is to see that these terms, as they are right now, they are actually dimensional. So this has the time unit in the denominator, and this has the time unit in the denominator elevated at the second power. Okay, so they are actually dimensional, and we want to get rid of this dimensionality. And this is done by introducing a dimensionless time. We define a dimensionless time, let's call it tau, which is going to be equal to t over a given characteristic time scale. So the whole thing is, the whole procedure is just basically having the expression in terms of the dimension time, and we apply the chain rule again, and then we can actually have this time scale in here 1 over t, and the derivative of it with respect to a dimensionless time tau. So we can do the same thing for the second order derivative in time. So what has to be pointed out is that this term here and this term here are dimensionless and are both in this case of order 1. So here we replace these derivatives by now these expressions. Now the idea is that we want to just have terms with non-dimensions. So the idea is to just reorganize this equation, okay? In a very, let's say, we can consider it a cruelest way, we can just start just deriving, let's be multiplying and dividing by terms. Let's do that. For example, imagine that we want to have this term isolated. So we will multiply everything by t squared and divide everything by r, okay? So we will have here d square phi dt square equal by t square r multiplied by minus bt d phi d tau minus t square r mg sinus of phi plus t square r multiplied by r t square sinus of phi cosinus of phi. Okay, so this equation is already non-dimensional. Okay, you can just do some simplifications. T right better just goes away, this with this here, this r with this r, and so on. You can reorganize the equation, and then we obtain something like this. Now, how do we analyze this? Is this of some help? Well, actually right now it is not, because what we want to do is to compare in which cases this term here can be actually or much smaller than the other terms. If this term is very tiny with respect to these terms, then we can actually make some assumptions and neglecting that term. But this way of non-dimensionalizing is maybe not the best way. A better way is to have these two terms that are of interest having some coefficients or some factors at the left hand side, and therefore we can actually multiply each term and this term by r and divide it by gt to the square. Okay, so we will obtain another non-dimensional equation, and this is what is obtained. So right now what we want to see, or we want to somehow impose that this term is very tiny in comparison to this term. So in other words, we can say that this bmgt is of order 1 and that this rgt square is much smaller than 1. Therefore, here we can already define a characteristic time. Remember that tau, so the non-dimensional time, is expressed, let's put in here, tau is equal to t over capital T. This is a characteristic time. But we haven't defined it. Right now we have the opportunity to define it because we have a relation like this. Therefore, we can say that the characteristic time is equal to T equal to B over mg. And then we can actually just put this definition in here, replace it, and then we will have the condition that we need. And the condition is actually not far away from our intuition that we had just at the beginning of the problem, that we had somehow a balance between the friction forces and the tangential acceleration. And this is, what is this? So this is means that the friction, which is B, just you can go in the slides and see what is this B about, is the one that multiplies phi dot, has to be larger than the mass, the gravity, and R. Okay, so in that sense you can actually express this system we just show in terms of a first order differential equation. If we cannot assure that this is actually fulfilled, then we have to consider the term that contains this phi dot dot, actually the tangential acceleration. Okay, so a second order differential equation, which means two first order differential equations, or in other words, a two-dimensional system. Okay. Okay, now let's go now with a very nice example in which we can study hysteresis and subcritical bifurcations. And this is done by means of this example of an insect outbreak. So there is this story that in Canada there is this spruce budworms that can completely defoliate a fir tree in just some years, 3-4 years. The idea is to see that if you are an observer of the population of fir trees, you can see that nothing happens, like you are like maybe some dynamics changing the amount of trees or the foliage of the trees, but you can see that suddenly it's like coming from out of nothing, you have a lot of spruce woodworms and the trees they just went away, so they completely like there is not any more trees. Okay, so this is called an outbreak. This is like this kind of situation we just saw before, that a parameter is changing and basically nothing changes in terms of the other system parameters, but suddenly everything is different. This is what the example of this subcritical bifurcation, if you remember. And this is an example, another example of this situation where you have a very dangerous bifurcation that in this case, in this context, is called outbreak. Here, two things are important in the model, as I will show you later. The first thing is that the spruce budworms, they evolve in a fast time scale, so the population can change pretty fast. While the fir trees, they change very slowly. I mean, they are trees, so they need years, tens of years to increase the number of the population. So if you remember, this is something we already saw, where we have this logistic growth. If you remember, just to make things clear, because it's easier to have it to put it in this way again, we have this n dot equal to what? To a growth rate of n and maybe a loss. So this is basically similar to the example of the laser, the same thing. Now the thing that changes is the way you model the growth rate. So in this case, the growth rate is just modeled as in our logistic example. Okay, so in that moment, this is just a given constant So the growth rate of the population when n is very small, so when this term is 0, the growth rate is equal to r naught. But then you change so n is changing, is increasing, and then you have a linear decrease in the growth rate until reaching the so-called carrying capacity here. And this is going to be term is going to be 0, and then you will have no growth rate. And something similar to alpha. This is going to be shown just in some moment. So we have now we have already the model for the growth. Let's say this one. So this term. Now this term. So in this case it's completely different, or it's very different with respect to the loss, for example, of the laser example. When you have the more n you have, the more losses you have. That was the example. In this case it's different. So you could think in this way, which should be fair. And this is something actually I do with the students, so we can discuss this in the meeting in MS Teams. So what is the relation we want to have here? We can have an n that increases, and therefore the predators increases, and increases, the predator increases until, well, infinity. Okay. Under the model, the scientists that work in this problem were considering that actually was nonsense. You cannot say that the predators that just grow forever. You don't have an infinite amount of predators. Okay. So under this one-dimensional system, when you consider just the independent parameter to be n, so the one that is ruling the system, governs p. But you can also put like a limit to p. You can say, okay, the predators, you have a limit, and you cannot have more predators. So the simplest model you can imagine is you start from 0, and then you just increase it until reaching a limit. Then in that case you will have maybe a lot of different individuals, or a large n, but still p will not increase anymore. So something like this. And this is actually the model that the scientists working on this problem were actually considering, and it looks like this. So this is just a function with this shape, and it's characterized by just a mathematical function with, let me show you. So this is the one. So we have just two parameters to control. So this b is gonna govern how large can be the number of predators, and a is like a value that denotes this like an inflection point somehow. Okay, so these are the two parameters that define this function. Okay, here again the definition of outbreak. In this problem, the budworm population grows suddenly from a low to a high level. And again, we have here the question of, okay, low and high, but what is low and what is high? So this is something we already saw in the case of the bead on this ring rotating. We have to somehow define a non-dimensional problem to be able to assign what is low and what is high by comparing terms. So the first thing we have to see is that right now it's not simple to actually know the dimensions or the units of different coefficients we see here. We have an R, we have K, we have A, we have B. But based on like a very simple analysis, we can see, for example, that you have a sum that makes some sense. Okay, so here you are summing two terms with the same units. This is how a sum is defined all the time. So it means that A has to have the same units of n. in the same way, we have this term here, and this term is dimensionless. Therefore, this term has to be dimensionless. In order this to be dimensionless, it means that k has to have the same units as n, so they cancel out. Okay, so we have here these three coefficients, n, a, and k. They have the same dimensions. We know that already. Now, the question is, we have to formulate a non-dimensional parameter, which means that we have to divide n either by a or by k. So you can actually do both, but you realize that you will have a very compact expression if you have defined x equal to na. Okay, this is, we choose it for convenience because the expression is shorter, you can see it. So this is the actual dimensionless formulation. We had decided that we will create a non-dimensional variable called n over a that was injected in the previous the dimension form, and we obtain, for example, this is going to be the term considering the amount of x with respect to the number of predators, so the loss, if you want to see it in terms of gain and loss, this problem. And this is the one that is associated with this logistic growth. Okay, so in order to keep collecting terms, we can do, for example, that this RAB that shows up, for example, in here can be just summarized in this R. K over A is going to be just K, for example, for this one. So like a dimensionless carrying capacity, if you want to see it in that way. And we have this one. Okay, so this is actually because it multiplies a temporal derivative. This can be associated with an actual characteristic time. If I just do this, remember that this is actually very important. We will do this many times. We have, so if you remember from before, we have dx dt is equal to dx d tau dt, and remember that we have defined a dimensionless time as t over a characteristic time t. Okay, now we have here this ab, so we will put just here ab. First, just let me just finish this. So this is what? D tau over dt, yeah, is 1 over t. So we have here again this dx dt, and now we just complement it with this ab. So ab dx dt is equal to ab 1 over t dx d tau. Okay, and naturally we would like to have this term here being equal to 1, so this being equal to 1. Therefore, we will just say t is equal to b over a. Sorry, actually is a over b. Okay, so far then we have obtained a dimensionless equation describing this outbreak of the worms on the fir trees. So this is the outcome of this analysis. Okay, so we have the equation. What do we do now? What is the idea of continuing with this analysis? Any ideas? Are you thinking behind your screens? Yeah, and as always is the case, there is someone telling me we have to do fixed points. We have to find the fixed points of the system. And how do we find the fixed points of the system? Yes, we will just consider this term in here being 0. And this happens when this term, when this term equates this term in here. By doing some graphical analysis, as I will show you in a second, we will realize, for example, that the fixed point at x equal to 0 is always unstable. But let me just show you these two terms, how they look like. Okay, this is how they look like. We have this expression in here, in blue. And something that is very nice from this function is that we don't have any coefficients in here. This is actually the parameter we're studying. This term, therefore, remains fixed, doesn't change. Now, this term here has two different parameters that can be controlled, okay? The first one is the carrying capacity, like the dimensionless carrying capacity. So how capable are the fir trees to host these budworms? This is the first thing, so this K. And R is the growth rate, how fast the budworms just grow, okay? And you will see that depending on the number of intersections between these two functions, we will have a given number of fixed points. Maybe some of you already realize that these functions, just to point out, are not exactly the same. So this is actually when you factorize x from this expression. So what we're doing here is to analyze the fixed points apart from the fixed point at the origin. We have a situation when there is a fixed point that shows up, okay, in here. This is something we already saw, this type of bifurcation. How is it called? Do you remember? So out of the blue sky, it comes a point that is half stable. Yeah, you see here. So this is a saddle node bifurcation. What happens next? Again, we can choose to move R or K, or both. And then we have that the half stable point here is splits in two. One is going to be an attractor, and one is going to be, one is going to be a repeller, and one is going to be an attractor. So from having just one fixed point, now we have three fixed points. It is quite interesting to analyze this. If we go back to the actual expressions of R, so R is going to be, or is equal to RA over B, and K is equal to K over A. So this is small k, okay? So there is two ways of changing these parameters. So how we change K? What is actually changing K means? It means increasing the actual carrying capacity of the forest, or decreasing A. So decreasing how fast the predators somehow reach the maximum amount. And the other thing is this R. So this is the growth rate. And the nice thing of this model is that it encompasses in this one variable three different effects. One is the actual growth rate of the budworm population, but this is counteracted by the predators, which is it appears in the denominator. So the largest the amount of predators, for example like this, the less the number of R. So the less this is growth rate. So what does it mean in terms of this? So it is like you can have a sudden, imagine the capacity of the fir trees is doesn't change, is something that remains like that for a long time, because this is a low time variation. But for some reason someone started shooting birds, okay, like, let's do some sports, and then the population of these birds dramatically, or not dramatically, just reduces a bit, and reducing the population means increasing R, and you can see that increasing this can already create an outbreak. Okay, as you are good students, and I know you are listening to these videos in a very attentive way, and I know also that you are curious, I want that one of you, when we meet next Thursday, show me this in Desmos, okay? How can you change R so that for a given value of K, so that you can create an outbreak, okay? So just someone of you that want to volunteer to do that, okay? Because the idea is to understand the next slide. So in this slide, this is already the whole function, okay? And you see that you have just the origin that is unstable and the corresponding attractor, but if you increase R, you are actually increasing this function like this. So at this point you have this half stable point, then this half stable point divides into a repeller and an attractor, okay? And this can be considered an outbreak already, because now you have, you see here, a B-stable condition. You have two possible equilibrium points that are stable. Unstability means hysteresis. And this is actually, some people call this already the outbreak, as I already told you. But I would say this is the actual outbreak, because you have here a B-stability point, okay? But still, if you have perturbations in any around this, or you have an initial condition in any of these regions, your solution will actually go to the fixed point that is associated with a small amount of budworms, a low X. However, if you keep increasing R, which means, as I pointed it out just in the previous email, in the previous slide, if someone has the nerve of killing birds, then the population will dramatically change, and you can have this going from this position that was very nice, that everything just goes to this fixed point, to a position in which any kind of perturbation will just go to this huge outbreak, so a very large number of budworms, okay? Now let's look this in terms of this bifurcation diagram. So everything is fine, you have your budworm, some equilibrium in our ecosystem, and here the population of birds start decreasing, but still we're in the fixed point, so nothing is happening, everything is nice. And if you have a perturbation of some reason in here, maybe for some reason the budworms have a high reproduction weekend, then it will grow, but it will go back to the equilibrium point, and we will maintain in this stability region. However, it's going to be at this point, this dangerous point, which is going to be the outbreak, when they actually just a little decrease in the population of birds, you will have this huge increase in the population of budworms. Then if you want to go back, you cannot just, if you just remove two birds, you cannot just put two birds back and expect to be back in the small population of budworms. You will have just to increase a lot the number of predators to decrease R, until reaching again this initial state when you just have a small amount of budworms, okay? So you see here there is a hysteresis problem that is actually omnipresent, is ubiquitous in nature. Okay, guys, so happy to having completed this video. So let's meet on Thursday, discuss about all the questions you may have about this. Hopefully someone will volunteer about this Desmos House of Gabe. And yeah, maybe I will start recording the next video. Okay, bye bye.